Let me share the screen.
So Mario is giving a presentation on the one-particle reduced density matrix functional theory. Mario is one of the leading experts on this method. Yeah, so Mario, the stage is yours.
Okay. Thank you, Christian, for the presentation, and thank you for the invitation. We talk about the 1RDM functional theory and its practical version we call the approximating of theory. Well, as you know, we have at our disposal the most efficient method nowadays is the density functional theory, but we also know that the list of problems of density approximation is still very large. For example, we have a big problem for describing strong correlation systems with DFT. So the main reason for this development is the need to overcome the drawbacks of currently used density functional approximations. The great advantage of using 1RDM functional theory is that the kinetic energy is explicitly defined and does not require the construction of a functional. So only remains to find approximation for the electron-electron functional. On the other hand, we also know that the 1RDM is a one-particle functional theory. Unlike in DFT, the necessary and sufficient conditions for the representability of the 1RDM are easily implementable. So our goal is to achieve a more precise formulas than approximate density functional, but less computational demanding than ab initio wave function basic methods. This is the outline of my presentation. I will give a brief introduction to the genuine 1RDM functional theory, and then I will explain the main approximation we do with the two-particle density methods in order to get a natural orbital functionals. In this part of the talk, I will try to present the state of the art of the current approximating of theory. Well, first, let me say the general considerations. I will focus on fermions, specifically on electrons, with Coulomb interactions, but I have to say that very recently, the foundation for reduced density multifunctional theory for boson has been given in these two papers, and the real problem right now is to find reliable approximation to describe system composed by bosons. Nevertheless, in this last paper, have been done the first steps in this direction. Next, I will consider only an integral number of electrons at zero temperature. So these systems can be described by means of canonical statistical ensembles. Here I have to say also that the 1RDM functional theory at finite temperature was developed in 2015 by Balsif, Kange, and Gross. And also we have studies for open systems at zero temperature done by Alcoba, Bocchicchio, and many others. And quite recently, an article by Gisbert and Krughaller was published for open systems at finite temperature for fermionic and bosonic systems. Next, I will consider only in this talk time-dependent 1RDM functional theory. The time-dependent functional theory was developed in all these papers. They used mainly adiabatic approximation and linear response theory. I have to say that very good results have been achieved for simple systems like H2 molecule. But I have to say also that it was established, for example, with these works, that the most used approximation, the GK approximation, are not able to give the evolution, the time evolution of the 1RDM. You need at least the GKL approximation to obtain the development, the time development of the 1RDM. I will focus also only on ground state. For excited state, you can find these papers, which are very close related to the time-dependent functional theory. And they are obtaining similar results only for simple systems like H2 molecule. Finally, I will focus on non-relativistic spring-free Hamiltonian. So the spin operators we commute with our Hamiltonian And for a system with a given value of the spin, we always have a multiplex. This is the Hamiltonian I would consider. As you see here, H represents the matrix elements of the one particle part of the Hamiltonian involving the kinetic energy and the potential operators. Brackets are for the two particle interaction matrix elements, and the A operator are the familiar creation and annihilation operators associated with the complete set orthonormal spin orbitals. Then these systems can be described as a mixed quantum state or an ensemble, which is described by n particle density matrix statistical operator. Here, omega are positive value, that's 1. So as you know, this operator is a weighting sum of all possible pure states. Typical example is the spin multiplex. For a given spin, we have 2s plus 1 energy degenerate eigenvector. So this kind of system can be described by this statistical operator, where we will take omega equal to 1 over 2s plus 1, because I will consider all the pure states are equiprobable. Well, the Hamiltonian, as you have seen, only have 1 and 2 particle operators, so the energy, as you know, is explicit functional of the 1 and 2 particle reduced density matrix. These matrices are given here by the contraction of the n particle density matrix. In the following, I will refer to these reduced density matrices just as the 1 and 2 matrices. And with this expression for the energy, we have, let's say, several methods without using the wave function. Then let's take a look at these methods. We have, depending on the fundamental variable, the density functional theory, the one metric functional theory, and the two metric functional theory. The great advantage of the two metric functional theory is that we have the exact functional, but we need to deal with the n representability condition of the two metrics. The alternative is to use this one particle theory. As you know, Hohenberg-Kohn theorem proved the existence of the functional, and a few years later, Gilbert demonstrated the existence for this functional for the one matrix in the case of pure states. Later, Ballon extended this theorem for ensembles. These articles here in this slide are the foundations of the 1RDM functional theory. Here is important the work of Levy, who demonstrates that the functional can be obtained using only the n representability condition, and we can forget about the v representability. It's important to say that both functional must match this exact functional of the two metrics. Well, let's take a look at the functional. We have the previous energy expression. Then from this expression, it's easy to see that the one particle part is exact because it's a function of the one particle density matrix. And the second part of the energy, which is a function of the two metrics, is replaced by a function of the one matrix. Here, this electron-electron function is determined by this minimization, in which we have to search for all n particle density matrix that give you this fixed trial one matrix, or you can also use this definition in which you minimize with respect to all n representable two metrics that contracts to a fixed one matrix. If you fix the domain in the pure states or an ensemble, you will obtain the Levy or the Ballon functionals. At the beginning, he was thinking and was conjectured by Ballon that these both functional are independent of the domain, but was recently demonstrated by Schilling that in fact they are not equal. On the other hand, we know from this article that these functionals in fact coincide on the set of the over-representable one matrices. So these are in fact the most important physical situation we are interested. Then if you use the constraining search and the variational principle, you will obtain the universal functional for the ground state. Here, the minimization is over all these one metrics in the domain of the n-representable one matrices. And we know the necessary and sufficient condition for the n-representability of the one matrix from a long time ago. They were established by Coleman in 1963. Okay. Well, we also know that the one matrix can be diagonalized by unitary transformation, which lead to the spectral decomposition of the one matrix. The eigenvalues are known as the occupation numbers, and the eigenvectors are the natural spin orbitals. In this representation, the ensemble and representability condition for the one matrix are these simplex equations, and the functional turns out to be a function of the natural orbital occupation numbers for a given number of particles. In the following, I will refer only to this representation in which the one matrix is diagonal. Let's see how we can find this universal functional here. Well, the first idea, of course, is to use the Levy constraining search formalism. He demonstrated the system of the functional by construction, so we can use also this minimization or the constraining search minimization. The main problem here is how we generate all proper n-electron density metrics that give you the fixed trivial one matrix. In principle, for limited situation, we are lucky because we can, for example, for system like periodic lattice system with periodic conditions, we can solve this problem exactly. In this slide, I show you these 5 papers in which this person have found the exact function for some simple models. But in general, this constraining search does not have an appropriate form for computation. Nevertheless, we can use this constraining search and also the property of the two metrics for determining the property of the functional. And this has been done in all these papers. So we now know how is the scaling, the homogeneity, asymptotic behavior of the functional, antisymmetry, pH symmetry, and so on. All these properties, of course, provide us a tool for the construction of the functional and for testing, which can be complemented with the S and N representability conditions. Unfortunately, so far, the exact function has been unreachable, and we have to settle for approximations. Before I start explaining the main approximations, and for sure I will forget some important papers, I will emphasize or highlight these review articles where you can find all the work has been done during the last 40 years in the NOF theory. Well, most of the, or practically all approximations we do in the natural orbital functional theory are based in this equation here. Remember, our energy functional depends on the natural orbital and the occupation number for a given number of particles, and we approximate the functional in this manner. This is the exact part of the functional, but you can see here a huge assumption. It's an important assumption because we are assuming that the energy function is linear with respect to the interaction between electrons. Moreover, you can see also that the two metrics is reconstructed only in terms of these occupation numbers. So we do not consider any explicit dependence of the two metrics in terms of the natural orbitals. And this is a huge approximation because we, in our approximation, we reconstruct the two metrics, but never we reconstruct the exact energy functional. And was established by Donnelly a long time ago, an approximate function still depends on the two particle density metrics. So I have to say that we are no longer, when we make approximations, we are no longer dealing with the genuine 1RDM functional theory, but we approximate natural orbital functional theory with the two metrics plays still a dominant role. And this approximation implies an important consequence for the N representability. Now, when you have approximation in NOF theory, the N representability problem has two sides. On the first side, you have to guarantee that the one particle density metric comes from the N particle density matrix. This is easy. We know the N representability condition for the one matrix. So here we have no problem. But we also need to guarantee that the approximate functional comes from the exact functional of the two metrics. How we construct the approximation? Well, by reconstruction of the two particle density metric. So the N representability of your approximate functional is close related to the N representability condition of the two metrics. Unfortunately, for the two metrics, a complete set of N representability conditions that do not depend on higher orders remains unknown. So we have to conform with an alternative to use only the some necessary condition that depends on the two metrics. For example, those conditions D, Q, and D conditions. Well, using the terminology introduced in this field by Eduardo Ludeña, we can say that we have two methods for approximating the functional, the top-down and the bottom-up method. In the top-down method, you propose some approximate wave function and you express the coefficients of this wave function in terms of the natural orbitals and occupation numbers. So you can obtain directly the energy functional, which will be by construction N representative. On the other hand, in the bottom-up method, you propose some reconstruction for the two particle density matrix, and you impose the condition you know for the functional, for example, the N representability condition, and in this way, you will obtain the functional. Let's analyze first the top-down method. As I said, we have a wave function, an approximate wave function, and by contraction, you obtain the two particle and one particle density matrix. Then the main problem here is how you express this exact functional, which is in terms of the two metrics, by a functional of only the one particle density matrix. Here I show you several articles where a wave function, approximate wave function, have been used in the natural orbital representation, and expression for the energy have been obtained. What have in common all these works is that the energy expression depends not only on the natural orbital and occupation numbers, but also depends on additionally magnitudes. The only exception is the Hartree-Fock approximation, where you use an isolated determinant, and the two matrices is expressed by an anti-symmetric product of the one particle matrices. And then you obtain the well-known functional for the energy in the case of the Hartree-Fock. To illustrate that, let me show you the case of two electron systems. In the Seglet state, for two electron systems, Lobding and Schur found long time ago the exact wave function for describing this system. You can observe here that this wave function depends on the natural orbital, the occupation number, but also on this phase factor that appear here in blue. And the energy adopt this expression. Well, this phase factor was found that for weak correlation regime, when the system is close to the Hartree-Fock case, all the phase factor can be taken as negative, for example, and only one will be positive with the largest value for the occupation number. However, when people studied the van der Waals effects in this two electron system, was found that always you will have different signs in the phase factors. Was demonstrated also that, that this alternated sign pattern is closely related to the long-range nature of the Coulomb interaction. So the thing is, even for this simple system, we have a lot of possible combinations for selecting the phase factor, and this is known as the phase dilemma. By fortune, this weak correlation regime gives us this value for the phase factor, and surprisingly, this functional with this fixed phase factor not only works well for the correlation regime, for the weak correlation regime, but also for all correlation regimes practically, and for the strong correlation regime. You can observe here that this energy for the two electron system depends on these L intervals. These intervals can be called exchange and time inversion intervals, and they emerge from the correlation between particles with opposite spins. On the other hand, we can also observe that this functional here is not a genuine one particle density matrix functional, because we know the expression for this selection of the phases, but we don't know how to express this energy in other representation. So in principle, this is just a natural orbital functional approximation, but we cannot say, even with this simple case, that we have the genuine one particle density matrix function. Now let's move on to the bottom-up method. Well, practically in the bottom-up method, all the functional proposals use a two-index approximation. This two-index approximation is used because, of course, we can reduce the scalability of the method, and we can obtain a better performance from the computational point of view. First, we have the GK-only functionals. In the GK-only functional, the two metrics is proposed in this way by this equation. It's quite similar to the Hartree-Fock approximation, but modified by this F function that depends on the occupation numbers. For singlets, this is expression of the energy. You see, it's practically the same like the Hartree-Fock case, only modified by the F function. Along this year, there have been proposed many kind of this functional. In this article, you can find all these GK functional that differ from one to other only in the way you approximate the F function. These GK functionals have been exhaustively studied in many benchmarking articles. In these articles, the result of the function have been comparing with the result obtaining with a simple model where you can obtain exact results, or for example, with the homogeneous electron gas or with a few electron harmonium atoms. And also there is some works where the comparison is for energetic properties obtaining from very accurate ab initio methods. What have been demonstrated with this in these works is that for any negative properties and in many correlation regimes, we can obtain reasonable good results. But also was demonstrated that these functionals violate significantly many of the properties of the functionals. For example, the simple antisymmetry. And also they violate a lot of any representability conditions. This is the reason why these functionals in many cases overcorrelate. The next step in the bottom-up method is to add the L integrals. To add the L integrals, we can use the cumulative expansion, in which the two metrics is approximated by the antisymmetric product of the one matrices plus some correlation to this, which is called the cumulative matrix or the pair correlation matrix. For singlets, this will be the expression for the energy. You see here a Hartree-Fock line expression of the energy plus some correlation energy depending of the cumulative. So the next step to obtain GKL only functional is to approximate the cumulative. In this article, it was proposed the approximation for the cumulative in terms of two index matrix delta and pi. These two index matrix, I'd say, satisfy many properties of the two metrics, symmetric properties, some rules, and also we have imposed some necessary representability condition for the two metrics, which give us these inequalities here that will define, you can define from here the delta and pi matrices. The expression for the energy with this approximation for the cumulant is given by this equation. You can observe that the Coulomb and exchange integral are modified by this delta matrix, and the L integral is modified by the pi matrix. I'm not going into details how we approximate these delta and pi matrices to give several functionals. You can find them in these papers. I have to say that of this GKL functional, the most successful have been those based on electron pairs. And in this case, what we do is we divide the orbital space into subspaces, and for each subspace, we will have only 2 electrons. It's important to say that why we do this? Well, because the electron pairs are chemically attractive. Practically all the bond theory is based on these electron pairs. On the other hand, electron pair condition allow us to simplify the problem for the occupation numbers, which is a constraint minimization problem. And with using this condition, we can transform this problem into an unconstrained minimization. And finally, I have to say that these functionals are the only functionals that give the correct number of electrons when you have a homolytic dissociation. You will not have the problem was addressed by Vectau in the first talk of this session. Well, using these constraints, you can rewrite the energy in this form. The first term will be the sum of the electron pairs energies, and the second one is related to the interaction energy between electrons belonging to different pairs. I'm not going into details. You can find them in the literature, but this is the expression for P NOF 5 and P NOF 7. You can observe that the pi matrix is quite simple. It's just a product of the square roots of the occupation numbers. And when you don't have this term here for the interaction between electrons belonging to different pairs, you obtain the P NOF 5 functional. This functional is just an independent electron pair model. Interestingly, the functional was obtained firstly using the bottom-up method, but later was realized by Cassia-Pernal that this functional can be also obtained from anti-symmetrized product of strong tonal geminals when you fix the phases. So probably the P NOF 5 is the only functional we have obtained so far using the top-down and bottom-up method in the natural orbital functional theory. And of course, is extremely n-representable. Well, so far I have addressed only single states. Let me say a few words about the multiplex.
Sorry, Mario, you have 2 minutes left.
Okay, I'm practically finished. I want only to say that for multiplex, we have found a way to simplify the problem, because the key factor is that for the whole multiplex, for this whole ensemble, the projection of the spin, the expectation value, is equal to 0. So we can use also a restricted formula even for the multiplex and obtain this energy, which is quite close to the singlets. Just one result obtained with these functionals. You can observe here that for this chain of hydrogens, 50 hydrogens, we can obtain very good results in the strong correlation regime. We compare here with the DMRG result, but in the equilibrium region for the P NOF 7, we have that the functional undercorrelate. To add the missing correlation, we can use the NOF MP2 method, in where you add the dynamic correlation using a correction coming from the MP2 method. Finally, I have to say that the problem here is a constrained minimization problem. And the main difference with the DFT or Hartree-Fock is that the error equation for the orbitals cannot be reduced to a diagonalization of the matrix of Lagrangian multipliers. During this year, many procedures have been proposed, and recently we have made available for the scientific community a code where we use a method proposed in 2009 where the orthonormality constraint for the orbitals can be guaranteed from the beginning, and the occupation number can be obtained from the using the conjugate gradient method. So these are the closing remarks. Let me say just that the challenge for the future is to describe the entire correlation without resorting to hybrid methods. And of course, we need to reduce the computational cost. There is a lot of room for improvement. Well, thank you for your attention.
Thank you very much, Mario, for this very nice and also quite comprehensive presentation. So you have time now for questions. Thank you. Please raise your hand or just directly ask Mario. I think there's one question by, let me see, by Yannick.
Yes, so first of all, thanks for the very nice overview. One question, maybe you could elaborate on the convergence behavior, because we've been working with RDMFT and also your functionals for quite a while now, and we find especially the orbital optimization to be quite tricky in terms of rotations, especially between orbitals from different subspaces in the pairing scheme. Could you maybe elaborate on that a bit?
Well, as you said, is this part of the optimization problem is the most difficult. In principle, you have in the method based on the difference of the Lagrangian multipliers, and then you optimize. But in principle, I don't see there are really great problems, because the orbitals adapt to this method we have proposed in 2009. So, well, I didn't prepare anything about the only thing I prepared was this here. I think you can find in the code that when you fix the occupation numbers, you then form this matrix that depends on the Lagrangian multipliers. But the tricky thing is the diagonal part, because from the conditions, or the optimum conditions, you cannot obtain the diagonal part of this matrix. What we do,
it's undefined, right?
That is undefined, but we found that if you put at the beginning of the iteration procedure the one diagonalization of the Lagrangian multipliers, and keep them from one step to another, then the method will converge always. The problem is with the orbitals that have small occupation numbers. It's a real problem also in the multi-configuration second system field methods. And there maybe the solution will be really slow go to the convergence. But in principle, you can begin with any partition of the orbital space, and at the end, the orbital will adapt and you will not find any problem for convergence. The problem is with the time you will consume to obtain the convergence. But in principle, you can see the code. It's open source. So I don't know if I answered your question.
Yep, thank you very much.
It's also Julia who raised her hand.
Yes, I have maybe a short question to the phase dilemma you mentioned. So if I understood correctly, you said the specific choice of phases, which was shown on the slide, also works beyond the recorrelation regime. Could you maybe explain why this is the case, and also how you would, in general, start to tackle the phase dilemma? Is there any approach?
You're talking about the phases, yeah?
Yeah.
Here in the, for example, in the 2-electron case.
Yes, but also then when you go beyond 2 electrons.
When we go beyond the electrons, in the case of the 2 electron case, we take for the 2 electrons this selection for the phases. But when you go farther for many electrons, of course you have the same problem. This function right here for the 2 electron case, for the pairs, is the same as I showed before. So these are the phases. And for the interpair interactions, we have taken all negative.
But why?
This, of course, will give you the lower energy. But you are right. In the first attempt, let's say, when I published this in 2017, I take the phases like in the 2 electron case.
Okay.
But we've realized it later in other studies with the Howard model that it's not necessary for the interaction term to take positive. Probably, I don't, of course, I'm not sure. In some cases, when you are in the van der Waals regime, let's say for the long range dynamic correlation, you need to take a positive phases, as was demonstrated in this paper by Shane and many others. It's the paper from the Barents group, and this also from Gisbert and Van Loven, that you need positive if you want to describe the correctly the 2 electron case. But this is important for a distance between the hydrogens and about 4 or 5 the angstroms. But in principle, of course, if you want to obtain the exact solution, probably you need to explore whole space of phases. But this is impossible. This is why we are not working in the genuine 1RDM functional theory. This is just an approximation.
Okay, yeah, thank you for your answer.
So there was another question by Eugene De Prince in the chat. So maybe Eugene, you directly would like to talk to Mario, maybe?
Sure. I was just wondering, I missed the beginning of your talk, so sorry if you already said this. But
you are
these
listening in all the time.
the JK and JKL functionals are does the 2RDM have the same structure as a doubly occupied CI 2RDM?
Oh, okay.
I'm asking, is that the case?
No. I know that the double CI is not the case. In the case of PENO5, probably, but when you introduce PENO7, you introduce these terms here. I think probably there is no wave function behind this. I will expect that the WCI will not give you this term because this expression is quite simple. In the WCI, I believe you have more terms. So,
but I mean the actual non-zero elements of the 2RDM. Are they the same non-zero elements in both cases?
But I'm not sure, but I believe that this is not exactly that the WCI. WCI probably is better approximation, of course.
I'm trying to understand what the best possible answer you could get is. Is it the doubly occupied?
No, WCI for sure. This energy will be on upper bound.
Okay, thank you.
I think.
Okay, thank you.
One very last quick question by Paul Johnson.
Sure. Sorry, I was just going to point out that, yeah, it's the same 2 matrix elements as DOCI. In particular, it's an approximation to APIG, which in the weakly correlated regime is not going to be DOCI. Yeah. Thank you very much.
Let us thank them.
Which you saw in the H50 curve is the point.
So in the interest of time, so let us thank Mario again, and then proceed. Let us then proceed to the final presentation of this session today.